Hi, we're from Group 5. Today our group going to present our video presentation for subject Structural Analysis and Design BNP 20803. This is the contents for today's videos, which is interviews, design process and project procedure, and calculation. We conducted interviews using surveys. We managed to get 3 engineers to share their viewpoint for our questions. The first interviewee is Mr. Azri Sidek, which is an engineer for 25 years at the MTD Construction SDN, PhD. The problems that always occur to implement the design and drawing to actual construction site based on Mr. Muhammad Azri Sidek is material in the design drawing may no longer in the market. Certain item may need specialist contractor to execute works at site which may design drawing not detail enough to follow. Design drawing not reflected the actual at site. Incomplete drawing, thus the construction team cannot proceed the works. Based on Mr. Muhammad Azri Sidek opinions and experiences, all related parties who produce detailed drawing to discuss before finalize the drawing for construction. Shop drawing or coordination drawing before construction. Search or survey the supplier before stated the material used in the design drawing. Discuss or submit method of statement before proceed works. Apply latest software in producing construction shop drawing, for example BIM, Revit. Next interviewee is Mr. ZAMZAN, which is an engineer and project manager who works at MTD Construction SDN, PhD, for 29 years. Based on Mr. ZAMZAN regarded problems that always occur to implement the design and drawing to actual construction site are the actual construction site condition is not reflected in the construction drawing. Type of design or method of construction as stated in the drawing is not suitable or practical to implement at site. Materials list in the drawing no more available in the market. Based on Mr. ZAMZAN opinions and experiences on how to solve the problems are required new site investigations such as soil investigation, survey work, mapping in order for engineer to review the design. Contractor can counter-propose the design and submit to client or engineer for review and approval. Pro-contractor can submit proposal which is most convenience to them in terms of cost, time and resources. Contractor has to appoint his own qualified designer to prepare the alternative design and drawing. This will be additional cost to them. The last interviewee is Mrs. Narashikan Ismail, who is a QRQC manager at MRT Corporation SDN, PhD, and have 27 years of work experiences. Based on Mrs. Narashikan Ismail, problems that always occur to implement the design and drawing to actual construction site are the disagreement between the structure, architecture, and M&E drawings. The majority of construction contracts use traditional processes such as fragmentation, or different design based on trade causing performance to hinder. Based on Mrs. Narashikan Ismail opinions and experiences on how to solve the problem is to merge all trades engaged by using BIM software or a BIM-based process. Next, strengthen team members' communication, cooperation, and coordination during the design and construction stages. Structural engineers are typically brought into a project by the architect or building designer and work on behalf of the project owner to evaluate and accept deferred submittals for compliance with the structural plans and specifications, monitor construction, and perform special inspections as defined on the contract. Conceptual design is the first step a structural engineer will take, is to go over the drawings created by the architect or building designer. To get an idea of the various uses of a structure, the engineer will consider a variety types of units on a larger multifamily project, or the variety of room uses in a larger single-family home or commercial structure. The structural engineers will evaluate the structure site-specific requirements based on its location. This will include a soil report to determine potential footings, the exposure category to which to design, applicable wind loads, and seismic considerations. Following the determination of environmental factors, the engineer will perform an initial design of building elements such as roof, wall, and floor layouts per architectural drawings, footings and/or slabs, bearing walls including beams and columns, and identifying potential mechanical, electrical, and plumbing conflicts. An engineer will begin with system design and work their way down. Understanding the structure's load path is critical, with particular attention paid to gravity loads, lateral loads, and uplift on the various elements within the structure. They will begin preliminary designs of various structural systems once they have a general idea of the structure's load path. Engineers will create preliminary designs for the roof system first, working from the top down. Then, depending on the number of levels and different unit types in the structure, the walls, including gravity and lateral force resisting systems, as well as any required beams and columns, will be designed, followed by the floor systems, and the process will be repeated as many times as necessary. The engineer commences the element engineering phase by ensuring accurate dimensions for the various components of the construction project through geometry coordination as defined in 2D or 3D CAD software. The engineer will start specific member analysis for the specified spans, such as calculating roof loads transferred to exterior and interior bearing walls. In general, lateral force resisting systems necessitate the most engineering time, when combined with window and door perforations that necessitate headers and beams. The engineer will be able to use this analysis software to apply a variety of loads such as dead, live, wind, and earthquakes. The engineer will be able to identify axial forces, bending moments, shear force, drag force, and combined forces as a result of this analysis. Once the forces are determined, the initial member sizing can begin, allowing the engineer to create a rough draft to refine in subsequent design steps. Engineers fine-tune the various elements into final structural element designs through an iterative process. Consider this to be repetitive in nature, with the end goal of an efficient design that meets the variety of requirements that the structure's configuration places on the path that the applied load must take to reach the ground. The engineer begins with a broad knowledge of the loads on individual elements, and then narrows the focus until each element, and eventually the entire structure, is engineered to safely transfer all loads, meet code requirements, and provide an acceptable solution that can be signed and sealed. The load paths are precise, specific, and dependable as a result of this process. Lastly, for construction administration, the engineer is frequently tasked with reviewing RFI and deferred submittals, obtaining code approvals, and preparing construction schedules. Roof trusses, for example, are regarded a deferred submittal. This means that the engineer allows others to create the designs, which are then sealed by a specialty or delegated engineer. The structural engineers will review the sealed designs, and either approves them for manufacture, or returns them for revisions. Aside from reviewing structural design conformance, engineers will also monitor construction progress on behalf of the client, and will frequently perform site inspections to ensure the construction process is progressing and product installation is error-free. A construction project is the result of a joint effort between the client, the architect, structural engineer, and the contractor. Other specialists, such as those in soil investigation, water supply, sanitation, fire protection, and electrical services may have also been consulted. Construction project have three essential phases, which is planning phase, pre-construction phase, and construction phase. During the planning phase, the owner, architect, and construction manager discuss what will be built, whether it will be approved by the jurisdictional authorities, and parameters such as scope and quality assumptions. For architects, this phase is known as conceptual design, and it is sometimes included in the AIA definition of architectural services as schematic design. Every project is influenced by a unique set of variables. Building a one-of-a-kind project, whether it's a creative office or a manufacturing facility, a custom home or a sacred space, involves a wide range of design issues and may necessitate substantial effort to obtain discretionary and environmental approval. During this phase, project architect will collaborate with a civil engineer to ascertain setbacks from property lines, easements, utilities, slope band analysis for steep lots, and other details. Construction manager manages and strategizes all design, permitting, and scope variables in order to establish a viable project plan. Professionals such as engineers and consultants are frequently retained early in the planning process so that their insight can be incorporated into the developing plan. Early planning steps should also include site and building assessment, early engineering evaluation, and entitlement and land use analysis to assess whether the owner is able to build what and where the client desires. Green building options should preferably be regarded at this early stage for incorporation into the project plan. During pre-construction, the contractor prepares several cost estimates, which is a tried and true industry approach that produces better results than the hard bid model. In developing the total construction project budget and critical path schedule, the general contractor's input on construction costs and schedule should be considered. This approach to budget and schedule is beneficial to the change order process later in construction because it reduces the possibility of change orders and budget increases. During this phase also, the construction manager will be preoccupied with his own set of critical tasks. During the pre-construction phase, his services include the retention of the entire professional team, the retention of the general contractor, the development of a total project budget and overall schedule, risk management, contracts and insurance, and other project organizational business. For construction phase, the project will be shifted into actual construction by a construction manager and a contractor. During this phase, the professional team's role is known as construction administration. The architect, all engineers, and consultants should be hired to perform quality control inspections, respond to requests for information, RFIs, review and approve technical submittals, and generally ensure that the project is completed as designed by the contract. Construction manager's services during the construction phase will include on-site project management, oversee quality control, monitor the contractor's safety program, ensure contractors perform per specifications, coordinate permits, technical inspections and testing and monitor RFIs and submittals to ensure they are on track. From administering construction contracts and managing the budget and schedule to certifying contractor progress payments and approving payment requests, his vigilance during construction phase services is essential to keep the project on track. Lastly is the calculations for our group slab and beam. This is slab at FS7. The X short span is 3.35 and E long span is 4.57. So we divided short span with long span to prove either the slab is one-way or two-way slab. The result is below 2, so it's mean that this slab is two-way slab. The slab thickness is 125 millimeters. The design action is 11.634 kilonewton per meter square. For this slab, we figured that it is case 4, which is two adjacent edge discontinuous. So we have to find their moment and shear in long and short span. These is the formulas for moment, shear and main reinforcement. After done calculating for moment and shear, Then we calculate the main reinforcement for this slab by using the main reinforcement formula to prove either the slab has compression reinforcement or not. We use the MSX 8.75 kN per meter as the moment, and figured that the slab does not have compression reinforcement. Then we proceed to find the reinforcement area by using formula area of tension reinforcement, and got 285 millimeters square. So from table, we conclude that the reinforcement is H12 to 50 for the top. For the shear force, we calculated the maximum design shear force by using maximum design shear force formula and got 26.75 kN. Then we calculated VRD and we got 63.1 kilonewton. And lastly, we calculated Vmin and we got 243 kilonewton. So from all the data, which is Vmin is bigger than Vn, means the slab is accepted. Deflection for the slab, we calculated the percentage required tension and reference reinforcement ratio to get the L per D. We got actual is 57.15 and allowable span is 87.80, which means allowable span bigger than actual span. So this slab is accepted. This is simply supported beam. Shear force diagram and bending moment diagram can be calculated using shear force formula and bending moment formula. Durability, fire and bond requirement for concrete cover. The value of minimum concrete cover regard to bond is 25 millimeters. The value for minimum concrete cover regard to durability is 15 millimeters. Minimum required access distance for R60 fire resistance is 35 millimeters. Minimum concrete cover regard to fire is 17 millimeters. Allowance in design for deviation is 10 millimeters and nominal cover is 35 millimeters. This is continuous beam. For case 1, which is all span loaded with maximum load. This is the moment distribution table for case 1. For joint 5, the end moment is minus 25.1705. For joint 7, 7.5, the end moment is 25.831. For 7 to 9, the end moment is minus 25.831. The end moment for joint 9, 9.7 is 20.583, and 9 to 12 is minus 20.583. The end moment for joint 12 is 17.074. This is the diagram for case 1. For case 2, which is all span loaded with minimum load. This is the moment distribution table for case 2. For joint 5, the end moment is minus 24.6195. For joint 7, 7.5, the end moment is 23.21. For 7 to 9, the end moment is minus 23.21. The end moment for joint 9, 9.7 is 18.119, and 9 to 12 is minus 18.119. The end moment for joint 12 is 17.817. This is the diagram for case 2. This is the shear force diagram and bending moment diagram for case 1, while this is the shear force diagram and bending moment diagram for case 2.